let's look at this one. We're going to find the local maximum and minimum values of the function f of x equal to x times e to the x. We're going to go through, find the critical numbers, and then we're going to classify those critical numbers. So well, how do we find the critical numbers? Well, that means we need to calculate the derivative and then look at where the derivative is 0 or undefined. So let's get our derivative. First thing we need here, derivative. And if we look at this, it's a product. It's x times e to the x. It's a product of two x terms here. So we have to use product rule. All right, so let's do our product rule. So we write down two copies of our product, x times e to the x times e to the x. Apply the derivative in the first one to the first part, and then in the second copy, apply the derivative to the second part, and then put a plus sign in the middle. We keep differentiating, and what do we get? We get a 1 here, so this is just e to the x, and then derivative of e to the x is just e to the x. So we have this. And we know that's fine for a derivative, but we normally want to try to factor this. And I always like differentiating an exponential function because normally we can factor out that exponential term. So there's an e to the x here, there's an e to the x here. I can actually factor that out. So we get e to the x times 1 plus x. It's a nice factored version for our derivative. All right, so that's the first part. Find the derivative. Then we want to look at where the derivative is 0 and where the derivative is undefined. And what is that? So we want to look at where the derivative is 0. And so with a nice factored version like this, we can look at just the individual factors. So I take and that's the first derivative, not the second derivative. So we want to know where the first derivative is 0. So I'm going to take my nice factored form here, set it equal to 0, and then I'm going to solve this for x. And when it's nice and factored like this, what we can do is we can set each of the individual factors to 0. So if I'm looking, I have this e to the x. I'm really thinking, well, when is e to the x 0? And the nice thing with exponential functions, they're never equal to 0. None. So this factor doesn't give us any of the solutions. Well, then I look at my other piece here, which is 1 plus x. I set that equal to 0. That one's easy. 1 plus x equal to 0. That gives me x equal to negative 1. All right, so we have one critical number so far, or potential critical number, x equals negative 1. We also want to check, is our derivative ever undefined? So if we look at our derivative, our function's always defined. There's no division by 0. There's no log functions. There's no negatives under square roots. So the usual suspects here. And then same thing in our derivative. E to the x times 1 plus x. There's no issues with division by 0 or anything. So our derivative is never undefined. So there's no contribution from the derivative being undefined here. So going through what we've seen, the derivative is 0 at negative 1, and that's the only place. That's our only potential critical number here. So then we just go through and just double check. Is this actually in the domain of our function? And it is. I can plug negative 1 into this. I can plug in negative 1 into the x term, perfectly fine. And then e to the negative 1, also fine. So negative 1 makes sense in here. So that is in the domain of our original function. All right, so sometimes we'll get a critical number or a potential critical number. It's not actually, our function's not actually defined there, so we can't have a max or a min if our function's not defined there. All right, so we found our critical number. Now we actually want to classify this critical number as a max or a min. So we have options: first derivative test, second derivative test. Let's do second derivative test. And you could also use first derivative test. Perfectly fine to do that. And honestly, that one actually might be a little quicker because we have to do second derivative here, and that means we got to do another product rule, and then we'll have to simplify it a little bit. But I mean, you know what? I changed my mind. Let's do first derivative test. Both options are fine. Perfectly fine. But let's do first derivative test. All right, so we found -1, so we plot it. We have our interval from -infinity to -1, and then from -1 to infinity. And we're going to look at the sign of f prime, and let's actually write this out. So we have e to the x as one of our factors, and then we have 1 plus x, and we're going to see what that tells us about f prime. All right, so the nice thing about an exponential function, e to the x, exponential functions are always positive. So this thing is positive on that interval, positive on that interval. Just like if we were squaring something. If we squared something, always positive. So exponential functions, positive, positive. All right, so that's easy. Then let's do 1 plus x. All right, so we need to use some test numbers now. Maybe like -2. That's in this first interval. Plug -2 into this one piece here. I get 1 minus 2 is -1. And we really just care about the sign, so negative. Then I go to my other interval. Now we want to pick something over on the other side. 0 is always a good one, if you can get away with it, which we can because 0 is inside that interval. Plug 0 into this piece here. I get 1 plus 0 is +1, so it's +1. And so what we're seeing here is we have positive times a negative is negative, and then a positive times a positive is positive. And so what that means for our original function f is we're decreasing on this side, and then we're increasing on this side. And so if we were going to do the first derivative test, well, draw in what you think the function might look like. Really rough sketch. So if we're decreasing, try not to cover things up too much. We're decreasing, we'd look something like that. And then it's going to kind of round out. Make this slightly better. So we're decreasing on one side. We know the derivative is 0 right at -1 because that's what we found up here. That's where the derivative was 0. So that's kind of gives us a more rounded shape. So we're decreasing on one side, and then it kind of rounds out and then starts increasing. And so what the first derivative test says is if you kind of draw in that look, looks like a local min, and that's what the first derivative test actually says. We have a local min. Now, we only found one critical number, though. And our interval is everything from -infinity to +infinity. So on that entire number line, we only found one critical number, and our function's continuous. So not only is this a local min, this is actually an absolute min. So we only found one critical number on that interval. Critical number, not critical interval, critical number on the interval in -infinity to infinity. All right. So we actually get a little bit more information there. Not only is this kind of locally, it's a low point on our graph, but actually at -1, that's as low as our function ever gets If we were to extend all the way out to the left and all the way out to the other side, that's as low as our function ever gets at -1. So it's actually the absolute min. And the reason being is because, well, one, our function's continuous, and two, we found only one critical number. Only one critical number. It was a local min, so it's actually the absolute min of our function. And so to actually answer the question, if we wanted the min value, what we would do is plug -1 into our function here. So the value here would be f of -1. Plug that in. Plug -1 into the original function, and what you end up with is -e to the -1. So that's as low as our function ever gets. And since we only found one critical number, and it's a local min, what that means then is there actually is no local max. So we found a local min, which turned out to actually be the absolute min, and then there's no maximum for our graph. All right, that's a good example. Kind of going through what this would look like just in general on a fresh problem here, but also sometimes to see what happens if we have just one critical number. All right, so I think we'll stop there with this lesson. And what we've kind of done at this point is we've built up all of the machinery now. We've been able to see how to locate where we might have a max or a min. We've seen all the necessary tests now to figure out if it's actually a max or a min. And what we're going to do in the next lesson is kind of put this to use with applied problems. So we're actually going to kind of have these word problems essentially where we have to construct the functions and that we want to optimize, and then we're going to use these calculus techniques to kind of help us locate, okay, where in this function do I have my maximum, or where in this function do I have my minimum? So kind of the next lesson is everything's been leading up to this. So we'll see you there. Bye-bye.